going to use black and white. Oops.
No, do the other one. Yes. Better like that.
Yeah, let's just use white. So you can see this, right?
Yeah.
Okay. Now this part is really easy. What we need to do basically is we want to calculate the length of optic fiber. Now, in the design of fiber optics, right, we are really interested in the length, you know, because you have a cable, right? How long should this cable be such that I can have good transmission and good receiving, right? So this is transmit, this is receive. So the length of the cable is very important.
Sure.
Good. Now let me open this one of the slides and show you. Now there are two main issues to consider, right, when trying to calculate the length. You have to take note of the power and the rise time. So the 2 points to note are power limited and rise time.
So what we call them? The main factor.
Yeah, factors affecting design of point-to-point fiber optic links. Look at factors affecting design of point-to-point fiber optic links, right? What do we consider when we are designing the fiber optic link, right? We can't just take any length.
No.
We have to make sure that we are dealing with the right length, right? And then we have to make sure that we consider the power loss. This is what we call power limited. And we have to make sure that we consider the rise time or bandwidth limited. Now, this power limited length is due to losses. You know, as we keep going along the length of the fiber optic cable,
more losses.
we're having loss as we are going, right? We cannot transmit here and expect to receive exactly the same.
No.
There will be losses, right?
Yes.
Now, we know power losses generally in engineering. There is power loss, even in normal electrical transmission. So, if we are calculating the length of the cable based on the power loss,
Right.
we call it power limited length, right? Power limited length, right? If we are calculating the length based on the rise time, we call it rise time limited or bandwidth. Now let me tell you the meaning of rise time. You see now, mainly due to response time of devices. Now let me show you something. Look at this.
Yeah, I know this.
We want to transmit light from one end to the other, right?
Okay.
But the original signal is electrical. I hope you know that. Like data, you know, like you say you have, like I have Sky now, and my speed is maybe 16 megabits per second, right? Bits is electrical.
Yes.
But we want to use light to transmit it. You see this? What do? We cannot transmit light alone.
No.
And we cannot transmit the electrical alone. If we transmit electrical alone, this is normal copper wire. This is normal fiber optic.
Yes, yes.
So we have to find a way to convert the electrical to light. We have to convert the electrical signal to light. And then we transmit that light And when we get to the receiver, we convert the light back
Again
to electrical. So you see now, this is like the light source. This is like the electrical source. The bits or whatever, right? Data source. This is an LED, light emitting diode. LED. LED. What does LED do? If you apply
should convert
a voltage, it will give out light.
Alright.
So the LED will convert the source to light. Alright? So we have the light will now go through the fiber cable, right? This is the main fiber cable. This is called splice. This is like to section the fiber optics, each section, small sections. The fiber optics is not just one long cable. You have sections because.
Alright. Is it like join?
Yeah, it's better because you have less losses. Instead of just sending it through the full line at once, it makes more sense to send it short and repeat, like joining, connector. So after a short while, break it and connect again, But in that way, you have short losses, small losses. If you add all the small losses together, right, it will be less than if you just use a complete length of cable on its own.
Okay.
Now, these are connectors to connect one end of the system to the other. When I get to the receiver side, what do? I use a detector.
Yes,
to convert back to
from light to
yeah. So if you have a question and he said anything like LED, if you see any word like LED, know that it's talking about the transmitter side.
Yes, should be.
Because sometimes it's not going to tell you this is transmitter time, rise time. It's going to tell you LED rise time. So you will know that LED means transmitter side, right? And then detector, if you use the word detector, it means
the
receiver side.
Yeah. Yes.
Good. So you see now LED or laser pin detector, Now let's now consider the power loss. Power loss model. Power loss. Power limited. Now look at this.
Yes.
This is like launched power launched. This means power that is launched. That's like transmitted power. Now, the connectors, there will be losses in the connectors.
Yes.
So there's a connector loss.
Okay.
So you see now, it has dropped from here to here. There's a loss. Right? Now, along the length of the fiber cable, there will be loss like this. See the loss?
Yes.
Decibel per kilometer.
Yes.
That means for each kilometer, this is the loss. So for 1 kilometer, it will be like 1. For 2, for example, now if the decibel loss per kilometer is maybe something like 5 decibel per kilometer, right?
All right.
For 1 kilometer, it will be 5 decibel.
Yes.
For 2 kilometer,
10.
it will be 10. Like that.
Like that, yeah.
So if the loss is A, for example, so for L length, it will be AL.
AL, yes.
That A is called attenuation. The fiber loss per kilometer is what we call attenuation. So it will get here. So the power, you see now, power started from here.
AL or A per L?
AL doesn't mean AL.
Alright.
What do you mean APL?
I mean A per L or A.
No, look. If I have attenuation as decibel per kilometer, right?
Oh, yeah.
So loss will be
I get
A times L.
Yes.
Yeah. So that means the decibel per kilometer multiplied by the length. Alright. So you see now, the power starts from here. There is a drop here, connector loss. There is fiber loss, and this is where the power is now. Now this is what we call safety margin. You have to create a safety margin. When I was explaining to them, Abdurrahman,
yeah.
I use a bridge to explain it.
Bridge.
Yeah.
Alright.
Now we have a bridge like this. Let's say this is a bridge. Right? Whatever, right? And then you have cars going through, blah, blah, blah. Now, I designed this bridge I know that if the bridge is totally full with cars,
Yes.
with the heaviest cars, right, it's going to be about maybe 10 tons, 10,000 kilogram
Kilogram. Okay.
on it, right? This is the worst case that can happen. I am not going to design this bridge to be able to withstand only this 10,000.
Should be more.
Yes, I should create a little more extra,
Yes.
maybe 12,000, right? That 2 extra is called the safety
All right.
margin.
To be in safe side.
Yeah, to be safe side, because you never can tell, maybe you just design for exactly that amount and suddenly something just come to increase it,
Yeah.
the bridge is going to collapse.
All right. Yeah.
So when we are designing, we do safety margin, right? That's why I was telling them the other time when I was teaching them that, like talk. They told me that my bandwidth is going to be like 16 megabit per second, but originally it should be like 18, but due to network fluctuation it can be 16. I mean, why are you taking safety margin from me?
Yeah.
Make it 20 so that I'll get 18. You get?
Yeah.
So they put a safety margin and they're trying to take it from me. So that safety margin is just added to be sure that we can be sure that we are safe. It's not going to ask you to explain it, so you don't need to explain. You just need to know.
All right.
So when you're writing the formula, it will be easy to write. Now, after the safety margin, I will not get connector loss again at the receiver.
Yeah.
There is connector at the transmitter, connector at the receiver. Connector loss again, and then this is now the receive power. You see? All the way from here, look at all the loss up to here.
Okay.
Good. Now, if we write the formula for connector loss, we just use one connector loss, all the connector loss together. C.
One C, you mean?
Yeah.
One connector.
So this is the formula. So that means transmitted power, right, is equal to the received power, right?
Yes.
Plus all the losses. Of course.
Yes.
Yeah, because transmitted will be what I receive plus all the losses.
All right. So plus.
Yeah, for example, if I'm sending maybe 20 watt and I receive 17 watt, right? What's the loss on the way? 3. So this is equal to this plus 3, right?
Yeah, sure.
Plus
is
core connection loss plus safety margin plus the fiber loss itself. What's the fiber loss? Attenuation times the length.
Yes. Right.
But because we are considering length due to power limited, we call it LP.
Okay.
Just to show that we are dealing with power.
Yeah, okay.
So, what are you
Did you
looking
see my phone anyway?
phone? Yeah, we saw your phone, right? We saw your phone. Okay, yeah. This is it.
Do you have a charger?
There should be a charger there. Alright, so
PT is PR plus
C plus
C the connector
loss plus safety margin plus the loss in the fiber.
Alright.
No, the loss in the fiber is the attenuation multiplied by the length.
Alright.
You understand now?
Yeah.
This attenuation is in dB per kilometer, right? Good. So let's see what do we have. Good. So from here I can get the length now because I'm interested in the length. So what's the length from here? PT minus PR minus C minus S over A.
Or A. Yes, okay, easy.
Yeah. So this is the length because the most important thing is the length.
Yeah, I want to get the length.
Now take note of this. What I want to write here now. We calculate the length, right? Using power
dB.
and rise time, right? Then we choose
Yes.
the smaller one.
The reason why.
What?
Why? That's what I wanted.
No need to worry about why. Just know that we choose the smallest one. The smallest one. It will not. It's not going to ask you why.
I think he asked.
No.
No.
Cannot ask you why. No.
Alright.
You will just choose the smallest one.
We calculate
Well, one reason I can think of is that the smallest one, we have the smallest loss. You know? The smallest length, we have the smallest loss.
Okay, yeah.
Yeah.
Good reason.
Right, so...
But can you go back to your note? I want to copy it again.
oh, the equation, right?
Yes. We calculate the length.
Using power, right? This is for power. I didn't do the rise time yet.
Yeah, alright.
Yeah.
Using power and
Rise time. Then we choose the smaller one. We choose the smaller one.
okay.
Alright, so let's now go to dBm and dB. You know this already, right?
I remember something from override.
Yeah,
Alright.
dBm and dB. Let me go back to black. Alright.
And the
Now we know dB is just 10 log of P out over P in, right?
yeah.
Now, if P in is equal to 1 milliwatt constant, right? Then we have dBm. So dBm is equal to what?
P
10 log P out over 1 milliwatt.
milliwatt
So we set the P in to be 1 milliwatt.
directly.
I'm
Yeah.
going to charge my phone.
There is no charger.
I didn't see that. I can charge my phone and then come back after charge phone. too.
Yeah, no worries.
Yeah.
Yeah. Okay, good. So we have this.
So any
If I give you a power, I say find the dBm,
I have to divide
just divide it by 1 milliwatt and that's it.
alright.
So you see now.
dV 10 log P out over 1 milliwatt.
So look at this calculation, for example, right?
Yeah.
The total gain of this amplifier is this times this times this, right?
Okay.
What's the gain of the first one? Output over input.
Yes.
10 over 1, which means 10, right?
10 yes.
10 goes into here and 60 comes out.
Yes.
What's the gain? 6.
Yes.
That's 6 times, right?
Yeah.
60 goes into here and 180 comes out. What's the gain? 3.
3 180.
So we have 3 here, we have 6 here, and we have 10 here, right?
Okay.
So multiply them together, you have 180, right?
Yes.
That's like 10 times 6 times 3, 180.
Alright, yeah.
Now I can get this guy now back in dB.
Yes.
I can say to get the total gain in dB now, what do I do? 10 log 180 over 1.
10 log 1
Because 180 is the output,
and
1 is the
input.
input. So my gain is 10 log 180
80
over 1.
1. Yes.
Right? They are the same unit, innit? Watt. Good.
Yeah, all of them.
So what I'm going to do now is
To calculate.
10. No, I just say 180 divided by 1, which is 180, right?
Yes.
Where's log? Right? Multiply by 10, innit? So you have 22.55, right? You got it?
Yes.
dB.
Alright.
I can also do it in another way. I can find the gain of each one in convert each one to dB and add all together.
Add. Yeah, okay.
So if you do the dB for this one, you have 10. dB for this,
Yeah.
you have this, and dB for this, you have this. If you add all together, you still get the same thing.
I understand it.
Yeah.
I know. It's mathematics.
So dBm, see, you can do dBm for all this, right? Let's do dBm for 10 milliwatt.
10 log 10 milliwatt
over 1
over
milliwatt.
1 milliwatt.
That's just like 10.
Yes.
Right?
Alright.
This is 100 milliwatt, right?
Same thing.
10 log 100 milliwatt over 1 milliwatt. But this is microwatt.
100 times
10 to power minus 6. Yeah. So 100 microwatt dBm is what?
10 log
10 log
100
times 10 to power minus 6 divided by 1 times 10 to power minus 3. So you do all this magic and you get your answer. Alright? So that's dBm.
Alright.
Good.
Question.
Yeah. This is how we always set the question. Always. Like look at some past question that I used.
Same thing, you mean?
Yeah, same way, same thing.
Alright.
Oh no, this is the third. This is the last question. I didn't have the third question scanned. Alright, so like this now, you say using simple point-to-point fiber optic link, show that the power. I mean, we just did this now.
Yeah, I first draw.
Yeah, just draw it, write the power equation, find the L. That's it.
Alright.
And write what each of them means. PT, transmitted power, received power.
Easy.
Yeah.
That's it.
Yeah.
Alright.
For a pin diode receiver, when the thermal noise is this, it will always give you this question too.
What he put here? I don't
Don't worry about it.
Yeah. PR is okay.
Don't worry about it. It's very easy.
Okay, I think I know how to do it now. You explain to me here.
Alright. Turn to black again. What is wrong with this guy? Let me not write in white, innit?
Okay.
So, calculation. Now, he's going to give you everything. In fact, this second part is so easy. He's going to give you everything. Like now, for example, he give you receive power at this bandwidth is equal to receive power at 1 plus 10 log B base 10. He's just going to give you this formula, right?
Right.
This thing means that the receive power at a given bandwidth B,
yes,
is equal to the receive power at bandwidth 1 plus 10 log the bandwidth. You know? So it's going to tell you blah 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 bit rate. This is bandwidth bit rate, right? You know, bit rate is the bandwidth.
yes.
Using the above equation, show that the loss is given by this. This is just too easy. Now, what you just do, just write this equation again in terms of B. Yeah,
LP of B.
Yeah. So I'm going to say, remember, LP was what? PT minus PR minus C minus S over A, right?
Yes.
So from here, I just say LP of B, right?
Yeah, alright, I got what you mean now.
Yeah, it's equal to.
In terms of B.
Yeah, this B only affects the receive power. So the receive power of B
So PR of B.
minus C minus S over A. That's it. Everything is just simple mathematics.
Now I bring this one potential.
Yeah, you know it, man. Why do you want
No,
tutorial?
I know math. Little bit.
I don't know what's fucking wrong with this guy. Okay, so I'm just going to say LP of B is equal to PT minus, instead of PR, I'm going to have PR of 1, right? Right? Plus 10 log B 10, right? Minus C minus S over A. Isn't it?
Yes, PR of 1 plus 10. Yes.
Good. Let's write this again well. I'm going to have PT minus PR of 1, right?
Yes.
Minus C minus S over A minus 10 log B base 10 over A. Do you agree?
I will write it. I will this way.
Yeah, you know this minus.
You mean you
is
do
here?
like two fractions?
Yeah, two fractions. This minus is here, right?
One side.
And then I brought this 2
Yes.
here over a. Then this, if it goes inside here, becomes minus,
Minus.
and the a is also in the bottom too.
Okay. Minus c. Okay. Cancel. Simple. B over a.
So let's see. What do you observe? What do you observe here between these two? This is LP of B, right?
Ah, this be R1.
Yeah, so this will be LP of 1.
Alright.
So when B is here, anything is here. That should be here.
Yeah, I know.
So this guy will be LP
LP
of 1 minus 10
Come on.
log B is 10 over A. That's it. LP of B.
So I proved it already.
That's all.
Alright.
I mean, Govinda is fun, man. Govinda's part is easy.
Not all the time. Not all the
But for this particular power consideration, I think this one is easier than the first part.
Alright.
He will always bring this in different ways. Like, look at. See? Same thing. Okay, this one is just calculation. Okay, this is calculation throughout. Evaluate the power limited length equation. Yeah, this is the first equation, and then we didn't do this yet. Look at the next exam. Do you see? Same thing. You see?
Alright.
Look at the other exam. Same thing.
So it will come in any way.
Yeah, it's the same way. I don't know whether that's the only thing he knows in this life. He keeps
Alright.
saying the same thing. It's very weird, isn't it?
No, it's easy to like recognize,
Yeah.
this thing is same as the first.
Okay, so we will now go to the next one now. Good. Optical and electrical bandwidth. We really don't need to bother much about this part, but I'll just explain it to you.
Alright.
You know this already. This is decibel, dB.
Yeah. Like
There is a point called minus 3 dB. There's a point called 3 dB point, or half the power point. It's actually the point where the gain is half. You see this now? This is like output over input, right?
yes.
If this guy is half,
Yeah.
that's the 3 dB point. Let's do log half and see. 0.5 log, right?
Yes.
Times 10. You see this? Minus 3.
Okay.
That's what you call the 3 dB point actually.
Alright.
Yeah, it's a very important point in electrical engineering, right?
What's
It's the point at which the power output
yes.
is half of the power input.
Oh yeah, I studied that in first year.
Yeah. That's what we call
Alright.
3 dB.
Yeah.
Yeah.
Okay.
So
3 dB is always half.
yeah.
Half the power.
Yeah.
Alright.
So that's just basically what you need to know here.
That's all the information, all the new information.
Yeah. So see now. So this is the
So yeah, here we can see.
optical 3 dB point, right?
Yeah.
But what you need to know about this is, okay, we know all this. All right, there's nothing here to talk about. Good, rise limited. Rise time. Now I told you that. Remember when I was doing this? I told you
This.
that we have some devices. We have diodes
Yeah.
in the transmitter side, and we have the fiber, right?
Connector.
And the receiver side, we have
detector.
detector to detect, right?
Yes.
All these things are electronic devices.
Sure.
You see, like, let me show you the circuit board.
No. It's impossible.
See what
My project. Be careful.
Don't worry, I can always connect them back.
Yeah.
Now, you see all these electronic components, right?
We should capture that to some later.
Yeah. This is a potentiometer, right? These are diodes. Now, these guys, right? They are electronic devices. They have what is called rise time. If you trigger them, like if I try to trigger this LCD now, it will not come on immediately. It will delay a little bit before starting.
Yes.
So if you give a signal to an electronic device, it does not just pick up immediately.
Yeah.
It will have to delay for a time before it will rise.
Sure. Like.
Yeah.
Graded.
Yeah. So that before it like this, something like this. Rise.
Yeah.
You know, this time to rise is called the rise time.
Do you remember TV? Old TV, it's like.
Yeah. Before it come on, yeah. So that delay, that rise time, can affect the length of the fiber optic, because it's also kind of losses too, you know. So it's kind of not exactly losses, right? But those electronic devices that you use in a fiber optic network can cause rise time effect that will reduce the bandwidth, you know, like bandwidth limited, you know. So yeah, we have issues with power loss, which we have already calculated.
Yeah.
Now we have something that can also cause bandwidth problem, which is rise time of devices, you know.
Can we say it's like losing time?
Yeah. So we can say that rise time of device is the time for a device, an electronic device, to respond. Response time will affect the bandwidth. Just put it like that. So it's actually called.
Yeah, because bandwidth is dependent on the time.
Of course.
Yeah.
So rise time or response time, you know?
I write it here again. Or
affects the bandwidth. You're right.
Affect
The bandwidth.
Okay, don't worry.
So what we need to now do now is that what we need to do right now is to now calculate the length using rise time, right? Now, you should know that if you have bit rate, right? If you want to get the period, you invert bit rate, right?
Say it again.
Remember when we had time that time? We
Yeah.
turn time upside down, you invert time to get bit rate. Remember for the first part, if you calculate the dispersion, which is time, you turn it to get the bit rate, right?
Yeah.
Like,
Here is
if I have the bit rate, I want to get the pulse width.
Yeah.
Pulse width actually means the period, the time.
Yeah. So if I do 1/140.
Yeah, you get this. But
Okay.
this doesn't matter, don't worry.
Yeah, I know what's mean. Yeah. No.
So actually, technically, rise time is the time for the signal to change from 10% to 90% of its maximum value. This is how to say it technically. The time for it to rise from the beginning around 10% of what we really want to 90% of the actual input. Or just say response time.
But it's clear, don't worry.
Yeah.
Yeah, it's okay.
For the device to respond. Good. We need to put some formulas in our head now, right? Now,
I know.
we have rise time of the fiber optic cable itself.
Alright.
Rise time, now that you understand rise time, we have to consider the optic cable itself.
So this one TS.
Yeah, this is like the overall, the total.
It's not mean this one.
No, this is the total of the system. Like, no, this is response or rise time of the whole system. You see now?
Total.
Yeah, you see now, it's given by summation of each of them. You see, this symbol, summation, add.
Alright.
So add the square of each of the rise times. We have rise time for transmitter. We have rise time for receiver. We have rise time for the fiber itself. Like this. Like this. Transmitter, we have rise time. T. Receiver, we have rise time. We have rise time for the fiber optic itself. So the total rise time of the system is that of the transmitter plus that of the receiver plus that of the fiber, right?
All of them square.
Yeah, because we said that T square S is equal to summation.
Yeah. Yeah.
Like from I to N.
So both of them the same meaning.
Yeah. So, but there's a particular formula you need to put in your head from here. There is a particular expression you don't need the proof, you just need to know it.
Alright, maybe I know it. If you tell me. Yeah.
This is it. We need to know the rise time of the fiber cable itself. So the rise time of the fiber cable, F, is 0.35 divided by FC over L. You have to put that in your score.
Okay.
So the other time Sultan was like, why don't you just write it like this? 0.35 L over FC.
Same thing.
Yeah. FC is called the electrical bandwidth. Take note. Electrical bandwidth, that's FC. Good.
FC is bandwidth.
Electrical bandwidth. Good. That's number one. I still do that. There are two things you have to put in your head. This formula and another one again that says that the bit rate, which is the actual bandwidth, is less than or equal to 0.35 divided by total rise time. Yeah, these are the two things you need to put in anywhere you want to put it.
My brain.
Calculator, your shoe, your socks, your brain, anywhere you like, man, or your phone. These two formulas are very important. Now, once you just know these two, trust me, everything is easy. Just to put them here and do mathematics, blah, 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 blah.
Okay.
So, what can I do now?
So, just one question. If C is not mean speed of light.
No. This is F small letter C. Like this is like subscript.
All right.
To mean bandwidth. This is not F times C. No way. Yeah.
All right.
They will give you FC in the question. Everything is very clear. That's why I like this type of question, because it will give you everything clearly.
Yeah.
So I'll just put them back into this formula now. Right? I have transmitter. I have receiver. Transmitter and receiver will just remain the same. The only thing that will change is the fiber. I'll just put this one. Which is what? 0.35 L over FC, right? Squared, innit?
Yeah, all of them squared, yes.
Yeah.
Yes.
From here, what's my tau S? Tau S is what? 0.35 over B, right?
Yes.
And if I square it, here becomes square and square too.
So yeah, alright, I got it. I think it's okay now.
Yeah. So
All of these equal.
yeah. You get the point now?
Yes, you can say yes.
Yeah, because they are equal to this.
Yeah.
and this guy is less than, we go to this, so I can write this guy, because everything here is the same thing as TL squared, which is this. You got it, huh?
Yes, but let me copy it.
No, just look at it.
Yeah.
Yeah, this is this is this,
Yeah,
this
clear,
is this.
clear. Don't worry.
Then
But
this guy,
like what you said, I have to
is-
know this.
yeah,
I can
Yeah.
substitute. already.
substitute and you know, just these two. But it's a bit easy because they both have 0.35 on top.
TS.
In fact, I think what is even important is not even this formula, is to just say TS is 0.35
Yeah.
over
I
B,
know.
because that's what we actually want.
Mhm.
Like this, these two, this and this. TF, TS. So we need how to get this. We need how to get this. We keep these two normal.
So 0. Should I put this sign smaller than?
Yeah, less than, greater than.
No. B.
Yeah,
All of them square. All of them square.
yeah. So once again, let me
Now what should we do?
let me write it clearly again.
Minus by 6.
Not dark enough. Let me write it in a more clearer way again. Right? TS less than or equal to what? 0.35
5
over
B.
B.
Yes.
So T square, right?
Yes.
Right?
Yes.
So when we do that, we come here and just this is the remaining part is mathematics. I'm trying to get this L. Right? But remember the L is for rise time.
LR.
Yeah, I'm supposed to put L.
So we
About
have LP and LR.
let me just finish. I'll put the L out later. You know.
Okay, no, it's clear. I will put LR.
So what am I trying to get? L, right?
Mhm.
I'm trying to get L in it. So I just say L square 0.35 square over FC square, right? And what do I do now? Less than or equal to
All of this.
0.35 square over B square, right? Minus, right?
Yeah, minus TT minus square root. Yeah.
Right?
Okay, I might I think.
So I'll take this FC up and this guy down, right?
Yes.
So I have L square is FC square divided by 0.35 square, all times what? 0.35 square over B square. I like to just combine these two together so that I can become plus. Right?
Okay. Let me do.
This is very tricky. We have to be careful here. Now, this guy will go into this guy, right? So this is like over 1, isn't it? Yeah, of course.
Yeah.
What's common between the B square, right?
Mhm.
What do I have here?
Minus B square times.
Right? Then I have this guy under, right? Innit?
Yes.
But remember, I'm looking for L, right? So what do? I take square root.
Yes. L.
Everything, innit? Once you get those two, once you can write this, and this, that's it. The rest is just how to put it together, calculate, blah 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 blah. Substitute, you know. So I can bring this b square out as well. And what I'll have left will be 0.35 square, right? Minus b square. In it.
So let me see.
I brought this b square out.
Yeah, okay.
Alright. Okay. I can do this like this again too. F c square over b square, right? This 0.35 will make this guy to be 1. I want to take this 0.35 into the bracket.
Yes.
So this guy will become 1, isn't it?
Yeah.
Yeah, this
Yeah,
is
because you divide.
Yeah, divide.
Yeah.
Right? Good. I can get the square root of this one. FC over
Take it out.
FC over B, right?
Yeah.
Root everything. 1 minus b square. So good. Now let's now try to. There's a special connection in this part.
Well, can you go back? I think I missed something. C over. Can you go back, please?
Up. I should go up.
Oh, yeah.
Here.
Here it is. Okay, we take it inside. Okay.
Are you talking of here?
Yeah, this one.
Don't worry about the way I do it. If once you start it, you can do it how you like. Just that when you are doing it, be looking at what you want to get at last.
Okay.
Because he will give you this. He'll give you this expression, right?
Okay.
Be trying to make it look like this.
Okay.
You know?
Yeah, I try to like make it tidy, no? Don't want to.
Yeah, I get it. Yeah, you see the formula always the same, right? See? You see? He gave it.
You give me everything.
Yeah. For this exam, I don't know, maybe other exam he didn't give it.
Other exam, no. Did he?
Yeah, but you don't need to prove. This is not proof.
Just
To solve. I think you don't have to cram anything. If you need to solve, he'll give you the formula. If you need to prove, he'll give you the formula too. So you are good. So that's that. Now, look at something. Now check this formula. This is I'm not write LR now, right?
Yes, but I think I started in something. I didn't know what.
Where?
Now from beginning we do these things, yes.
Yeah, okay, let's go from beginning here, right?
Alright. Then you said we should take L.
Now look, I took this, I left,
Yes, I take.
I square this part, and then I take everything to this side.
Okay, I did that.
When I take everything to this side, I now group these two together, brought out the minus so that they become plus, right?
What I missed here then?
What?
Was this one? I thought, yes, okay, you know.
Alright, so, and then I take this F here, take this guy down.
Yeah, alright, I'm this step now.
Man, this is simple mathematics.
Yeah, but because I forgot to write this one. That's why I started.
Yeah,
why
yeah.
I missed something here.
Just calm down, you know that it's easy.
So FC over 0.35 all times 0.357 b square minus tau square t plus 3r. Alright. So we do it in same
Square.
Oh, sorry.
No, yeah.
Same if I do.
No, man, no, that's
No,
not
no,
same.
no, this is square.
Yeah.
Yes. So then, what we did here? Because I do on one fraction,
Yeah,
so it's 0.35 square, that's 3 times.
you're not squaring the FC.
Oh my god. So I'm square. So this time this,
Yeah. Tau T square plus,
r square,
yeah,
uh,
everything divided by B square, right?
square, yes.
You have this guy outside.
outside.
This is square over 0.35 square times, yeah, good. So I just take, what do I do now?
Now we take like a common factor
Yeah.
outside.
Yeah,
What?
I'm just going front and back, you know, take this guy back,
Yeah.
take this guy inside.
Take this one goes inside.
Yeah, this guy comes inside, this guy goes back, so that this guy can divide this and come under here.
You mean
So
like
here can remain 1.
it's like that and B?
Yeah,
outside.
yeah.
Alright. So it's FC squared
Over B,
squared.
yeah, then 1,
1 minus B squared.
yeah, divided by 0.35 square. The rest is now easy from there.
So I divide both sides by 0.35 squared, yes?
Yeah.
Okay.
Fact, I used to think that you will move to cram. It gives you everything. I mean,
Yeah, but it's good to understand, you know, if you
yeah, so if it gives you everything, all you need to know is just to know that this square is equal to this square plus this square plus this square. That's it. It gives you this, it gives you this. What else? Just to calculate.
Alright. But this is good to show everything. you know,
Yeah, sure.
Like to prove, you know.
Yeah.
So now I bring square root of LR square root of minus B squared plus
0.35. Put your FC over B outside.
Oh,
Calm down, man. Now, look at this formula now, right? When B is going towards infinity, you know this sign?
infinity.
Yeah.
That's
So I'm talking of B maximum now. The highest bandwidth, right?
alright.
If the bandwidth is increasing to maximum,
Mm.
what should happen to L? L will be going to 0.
Yes.
Yeah, if this number is getting big,
FC is
whatever these things, I don't care. But once this one is getting big to infinity, this guy will go to 0.
0 is
Now, for this guy to go to 0, everything in the bracket should be 0. Everything in the square root should be 0.
say it again. If
For this whole expression to be
Be
going
0.
towards to 0,
yes.
everything in the square root should be 0.
Yes.
Like square root of 0 is 0.
0,
Yeah, so 1 minus b square tau square t plus. Sometimes you can stop here. There are some of the proof that's just to get there, right? Yeah. You could stop here if you want.
Yeah.
So we already got here. But then you could take it further. Right? Equal to 0.
Okay.
This b now is a special b, is the b max. You see now? So b square max, if I take this guy to this side now, you get that? Tau square t plus tau square r divided by 0.35 square be equal to 1, innit?
Okay.
You agree?
Yes.
Take care.
Yeah.
They're both equal, right? So this guy comes here. So what's b square max? Is 0.35 square divided by.
T.
So this is the maximum bandwidth that we can get. So if I bring it back to this formula, you see now. Check, compare this part. Compare this part
Yes. What?
with this part. They look the same but turn upside down.
Yes.
Do you see this?
Yeah.
So I can write LR as what? FC over B root 1 minus, right? B square over B max. You agree? This is like invert, this is like upside down of B max. Come on man, look at B max.
Yeah, but what you wrote down? LR equal?
Yeah, the same formula, the same thing,
Yes.
the same thing, but just that this part,
Over. Okay.
this O part is 1 over B max. Yeah, so it becomes B square over this.
So did he ask about that?
No, you just need the notes, you know? Where is the slide? Yeah, like this.
Alright.
You know?
Okay.
Just know that this part
This,
is 1 over B max,
B
max square, that's it. And then you know, square root I can write half on top instead of square root, right?
What?
Instead of writing this square root here, I can say everything to power half. You know the same thing?
Yeah.
Yeah.
Alright.
So yeah, so this plot now, right? This plot is showing that if we calculate the length, using power loss, this is a plot we'll get. If you calculate the length using the rise time, this is how it will go. You know, this is where they meet, and this is the maximum bandwidth. I don't think you need this information. So this is what you normally bring the question. It's either it tells you to prove it or it tells you to calculate. It's so easy, just to calculate the length. This is electrical bandwidth, this is normal bandwidth, this is rise time of transmitter, receiver, everything is the same. So we'll do it now. Now, oops, space gone. New, let me start a new page. Alright, so question. Now let's read that question carefully. Or let me even use this one that's clearer. See this question, right? See this one too? Same thing. This one too? Same thing. Which one do we do?
All of them the same?
Yeah. Let me start from the third one.
Alright.
A graded index, blah blah blah. Fuck the talk. Forget about the talk, right?
What's that?
Don't worry about it.
Okay. Okay.
Khalifa. Hello. Yeah, how's it? Yeah, fine. No. I'm not with my language. Yeah? Okay, no problem. Yeah, I will try. Yeah, no problem. He said he sent me Glenn something. Okay, so let's see. Now,
Glenn or Cohen?
Glenn, the attenuation of the fiber is 1. So that's A, right? A. They already give us that, right? Electrical bandwidth 900 FC mega. Megahertz dot kilometer, right? Length, maximum, calculate the maximum link length for a bit rate of 30 megabit per second. That's B, right? So B is equal to 30 megabit per second at error rate of 10 to the power minus 9 for the following specification. Don't worry about that. Now, look.
I have attenuation 1 dB. I have FC 900.
Yeah. Don't worry about this error rate. Don't worry about
Oh,
this.
okay.
Laser diode. I'm talking of transmitter now.
Yes, laser.
Yeah.
LTR.
See now, this guy wrote T. Laser diode.
No.
TT, transmitter.
Because it's from Julian.
Yeah. See, this person missed this one. You missed this. Who wrote all this?
I don't know, it's not my.
You missed it. This is bullshit. You see, this is the problem. No, you don't. They don't know. You missed it. So laser diode is the transmitter.
Mm-hmm.
Rise time is what? 5 nanosecond, right? Which is 5 times 10 to the power minus 9 second, right? Receiver. Okay. Power launch. This is transmitted power, right?
Yes. PT.
So PT is 5 microwatts, which is 5 times 10 to the power minus 6 watt, right? Pin detector. So this is the receiver. Receiver time is 1 nanosecond. 1 times 10 to the power minus 9 second. And connector loss C is equal to 3 dB, right? S is equal to 6 dB. That's safety margin. Look, minimum power received. This is anytime you see this dBm.
Yes.
Know that it's PR of 1. This is PR of 1 minus 60 dBm. Take note. This is very important. This last one.
9 second. Which one is
So
this one? No, this one total connect. Let's see.
C, yeah, connector loss, mass safety margin. They are all clear there.
See.
So easy. I just calculate the length. L for power is what? What's it again?
PR of 1. Give me a second. I want to ask. 6 minus 60. Is it always the same number?
No. It's not the same. But just know that once it tells you dBm
Yes.
at the end, that's PR of 1.
Okay.
Now what's LP that time? LP is P transmitted, right?
We should solve it on both sides.
Yeah, you do power and for rise time.
Okay.
PT minus what? PR of 1, right?
Yes. Minus.
PR of 1 plus 10 log B10, right?
Yeah.
Minus
Alright,
C minus
I
S
understand it exactly.
over A, right?
Mm-hmm.
Yeah, I'm using this formula
Yeah.
for PR
Okay.
or B, you know.
So
So
just was it LP or LP of B or I don't know.
yeah, okay, LP, yeah, LP of B.
So
Yeah, to make it look now, yeah, LP of B. So I can just say LP of what's the bandwidth? 30. So I can say LP of 30. You know? Transmitted power is 5 times 10 to the power minus 6 minus received power of 1 is minus 60, right? Plus 10 log 10. What's B? 30 times 10 to the power 6. Right? Minus 3 minus 6 divided by 1.
So P.
So just blah 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 all this.
So we don't convert PT.
Sorry. I have to do this to DB.
Yeah, I just try to first.
Yeah,
okay,
yeah.
Okay. Well, we can say is PT equal 5 microwatt. So that's mean MdBm equal 10 log 5 10 log
Yeah,
10 log 5 times 10 to the power minus 6
yeah.
over 1
Times 10 to the power minus 3. Convert this, please. So,
Okay.
right?
How much is the other?
I don't know. So what did we get? So remember to convert this to dBm, right?
Yeah, I converted already. 10 minus 6 16.22.
That's what you got?
Yes. I did 20 minus 23 dBm
Okay.
plus 60
So you got how many? 16 point what?
16.22. Is it possible?
22. I don't know, maybe that's what you calculated.
Alright. Yeah.
So we now calculate the length again using rise time. L is equal to what? FC over B root 1 minus B squared
So as a calculation, you said we take the shorter.
Yeah.
First part.
Yeah. I think we need to calculate this first part again. I need to erase this part out. You know, this Govinda guy is very funny. The way he does the calculation, we have to follow. Good, so
Should I erase all of this?
no, not so. It's not like so bad. So PT, right?
doing.
Yeah. Okay. So PT. What did you get for your DBM for your first one? No man.
Alright.
So launch power is actually 90 microwatts. That was a mistake there. Launch power is 90.
90 microwatt. So I put in blue again.
So do this again.
So now,
So we take this to dBm, right?
yes.
So that will be 10 log 90 times 10 to the power minus 6 divided by 1 times 10 to the power minus 3, right?
Yeah,
What did you get there?
minus 10.45.
45 dBm, right?
Yes.
So we just put it here. Minus 10.45, right?
Yes.
Minus 60 plus 10 log 30. This is what you're supposed to do.
Yes.
Minus
3
3
minus 6
minus 6
over 1.
divided by 1.
So
So 25 point.
77.
Good. So we now use rise time now, right? What's our FC?
900 maybe.
FC was giving us
We got capabilities.
900 electrical bandwidth, right?
Yes.
900 times 10 to the power 6 in it.
Yes.
Then the normal bandwidth was given as well?
30.
30, yeah. Square root of 1 minus 30 square 30 times 10 to the power 6 square, right? Times rise time for the transmitter. For the transmitter, I said it's for the diode, right? Which is this. So that will be 5 times 10 to the power minus 9 square, right? Plus for the receiver,
Oh, receiver. 1 nanosecond.
1 times 10 to the power minus 9 square, right? Divided by 0.35 square. Big number. So what we'll do, we'll get the smallest one.
Mm, 900 or so on calculator should I put this array
Put what?
text?
You could do it separately, small bit by bit. You could, like Abdul Raham knows how to type it long once. If you like, you can do it gently, step by step. You will still get the answer. What matters is the answer, innit?
Yeah, if I do everything okay.
Well, I think you should get something around 24 point something.
I don't think so. I get
Anyway, whatever you get, just take the smallest one. That's it.
alright. Just try to
Yeah, so the answer to this was 24.27.
Which is shorter.
This is shorter than, what did you get before? Than 25.
7.
So we use this LR is equal to 24.2. That's it. So, summary. I know this is what you like. Summary. 1. Point-to-point design consideration. We have power, limited length, right?
Yes. And time loss.
Yeah. And what?
Time.
Rise
Rise time limit.
time or bandwidth. Right? This is caused by a power loss, right? This one is response time of what? Devices, right?
Yes.
Now for the first guy, we have that the length is transmitted power minus received power minus core loss, connector loss minus safety factor over attenuation, right?
Yes.
And then we have that P received at a bandwidth is P received at 1 plus 10 log B, right? And then LP of B is LP of 1, right?
The plus 10 log.
Is it minus? Or I think it's minus. Yeah, minus. So these are the formulas we need to calculate. So then I can write LP of B, right, as PT minus PR of 1. Is it not?
Yes.
Plus 10
log
of B minus C minus S over A. I just replace this guy with this guy, right?
Yes.
This guy with this one. So for rise time, we have to know that the system rise time is transmitter
plus
receiver plus fiber, right? And they will give us the fiber as 0.35 over FC over L, and they will give us this guy as less than, right? So we just put them back into this formula.
Yes.
Yeah, just say
less than or equal.
right? And we solve. for L, right?
Okay.
So we finally get L as over.
0 point square.
So you will be given all the formula you need. Alright. So then the question will now be calculate length, right? So first do for power limited range, right?
Then
You have L equal to LP PT minus P R of 1
minus
plus 10
so
log B, right? Minus C minus S over A. First of all, convert. Make sure
to convert.
PT is converted to dBm. Right? This guy is always give you at the end. Like here,
Give me say minus 60.
this is P R of 1. This is P R of 1. This is PR of 1. So once you just see minus something, they just know that is PR of 1, you know?
Okay.
Don't worry about the rest. So when you get that, you just convert your PT first, then you put it 10 log B, just take the boundary as it is. It will give you connector loss, it will give you safety, it will give you attenuation. So you get the length. After this, you do for rise time. We know that LR is FC over B with 1 minus B square tau square T plus tau square R over
0.5
square. So this guy is for the transmitter, receiver. So for the transmitter side, we have things like laser, LED, like that, right?
Yeah.
For the receiver side, we have things like detector, pin detector, or whatever. But really, it doesn't really, because you have to square one, square the second one, add them together. So sometimes even if you make mistake, it's still the same thing, you know?
Yeah.
Yeah, but you should be able to know that this is actually the one for transmission receiver. But just like 2 plus 3, 3 plus 2,
Same thing.
same thing, you know. This is bandwidth, this is the electrical bandwidth given to you, this is normal bandwidth. You calculate the two lengths. So you now get LP, you now get LR. Choose
The shorter.
the smaller one.
Or the small.
That's it. Easy, right?
Yeah, better than the first.
Yeah.
Alright.
Okay, so good luck to you all.